All right, folks, this is video 2 in a series of 4 videos responding to your 3-2-1 survey on Chapter 5.4, Curve Sketching. You requested another example of a curve with asymptotes and how to sketch it. In the previous video, we used everything we could about f to find out asymptotes and intercepts. And in this second video, by the end, you should be able to know how to find critical values for our function, find intervals where the function's increasing, decreasing, and find the relative or local extrema, meaning local minimums and local maximums. So just to recap, this week we've learned a checklist for graphing functions. I use f to find asymptotes, intercepts, and continuity intervals. I use f prime to find out where my function's increasing, decreasing. I use f double prime to find out concavity, and then I combine all of this into one graph. We're going to focus right now on just using f prime to find critical values, monotonicity, and relative extrema. So here's our example, x squared minus 4 over x squared minus 1. I want to find what the critical values are, places where my function is increasing and decreasing, and relative extrema. So you'll recall that a critical value happens is when f prime of x is equal to 0 or does not exist. So where is this function, where is its derivative equal to 0? Well, we have to find the derivative first. So f prime of x, this is going to be a quotient rule. So I have low d high minus high d low over the square of what's below. So low is x squared minus 1. D high is 2x. That's the derivative of the numerator. Minus high is x squared minus 4. D low is again 2x. That's the derivative of the denominator. And this is all over the square of what's below. This rhyme is kind of silly, but it always helps me to remember which one comes first, right? I, for a long time, couldn't remember, is it fg prime minus gf prime or the other way around? And so remembering this rhyme, low d high minus high d low over the square of what's below, helps me to remember which order it comes in. So I want to know where this thing's equal to 0. So to do that, I need to expand the numerator, factor things. If you do that, you'll find out that f prime of x is equal to 6x over x squared minus 1 squared. So where are the zeros of this thing? This is equal to 0 if and only if its numerator is equal to 0. And so that means that x has to be 0. So that's the only place where the derivative is 0. Where is it undefined? It's undefined at plus or minus 1. Technically, these are not critical values because they're not even places where the function's defined. I will consider them very important values. So I'll say that there's a critical value, so a crit value at x equals 0. And also, let's say my function's undefined when x is plus or minus 1, because I still want to consider those points. The whole point is that only places where the derivative is 0 or only places where it's undefined, these are the only times that the function can change its sign, or rather the derivative can change its sign. On those intervals, it's constant sign. So I only have to check. So I'll write ID table here, because we'll have a couple tables floating around. If you're doing this all at once, you'll have a couple tables. I want to check the intervals around these points. So from negative infinity to negative 1, from negative 1 to 0, from 0 to 1, and from 1 to infinity. So my derivative should remain constant sign on these intervals. So I only have to test one point on each interval. I'll choose a point that's easy to plug into f and determine whether it's positive or negative. In fact, so I know that a lot of us like to actually plug values in, right? So maybe I would choose negative 2 and 2. I try to choose like small integers because it's easier to plug in. If I can't, I try to choose a small fraction. But sometimes we actually plug these values in. I think it's easier, actually, if I factor this thing. So this is what I mean. If I look at 6x, the numerator of this function, and then x squared minus 1 squared, and then I know that f prime of x is just the quotient of these things, 6x over x squared minus 1 squared. And so if I'm interested in knowing whether this thing is positive or negative, I really just have to know if this is positive or negative, and if this is positive or negative, and then divide them, right? A negative over a positive will be negative. I'm really just counting signs. So the reason I split it up like this is because if I'm not going to use my calculator to graph something, then I kind of want to be able to find out if things are positive or negative without actually using a calculator too. I only care about whether these are positive or negative. So -2 times 6 is -12. I don't care what that is. It's just negative, right? -1/2 times 6 is -3. I don't care what the value is, just that it's negative. And then 1/2 times 6 is positive, and 2 times 6 is positive. Here's where this method actually really shines. X squared minus 1, no matter what it is, as long as it's not 0, and I've excluded those points here, is always positive, right? Take a number, square it. That number is either 0 or positive. And so I know that this thing is positive down the board. And so I only have to know what's happening with 6x. That's it. And so if I count these signs, negative over a positive will give me negative. Negative over a positive will give me negative. Positive over positive is positive, and finally positive. Now, I agree that this might take a little longer to set up, but if I don't have a calculator, or if I'm told that I can't use a calculator, this is certainly a better way to do this because I don't have to deal with large numbers. So what does this mean about increasing and decreasing? Anytime my derivative is negative, I'm decreasing. Anytime my derivative is positive, I'm increasing, because that means I have positive slope or negative slope. So here I'm decreasing, then I'm decreasing, then I switch to increasing, and finally I continue to increase. I'm going to be a little bit careful. I don't actually have to be in this example, but on other examples, I want to be really careful when I choose something because it's a point of discontinuity. So -1 and 1 were points where the function was discontinuous. They are not candidates for maxes or mins. So I'll indicate this maybe by drawing a dashed line. You can draw a dotted line, or even just write in the words, this is a point of discontinuity, just so that you don't make the mistake if I switched increasing or decreasing here. I don't want to accidentally conclude that this is somehow a point that's a relative max or min. So where do I have maxes or minimums? I switch from decreasing to increasing here. So it looks like this. And so this is a local min. Where it looks like at x equals 0. That was actually one of the intercepts that we found earlier. It's the point 0, 4. And so now I'll interpret these tables for you. So what I've learned is that f is increasing on the intervals 0 to 1, united with 1 to infinity. F is decreasing on the interval -infinity to -1, united with -1 to 0. And finally, I have a local max, or local min, at the point 0, 4. So that's all the information that the derivative can tell me. Just to recap, I first had to find a derivative. I simplify that derivative as much as I can so that it's easy to find the zeros. For a rational function like this, I look for zeros of the numerator. That tells me where the derivative is 0. And zeros of the denominator to find out where the thing is undefined. I found out that critical values were 0, and I had undefinedness at plus and minus 1. I put those into intervals here and just checked the sign on each one. I think it's easier to look at different factors of this, but you could certainly plug into the function.